In integrated circuit manufacturing today, engineers need to ensure the polycrystalline lines on the wafer are perfectly straight up. There are millions and millions of these tiny lines within a square millimeter area, and these billion-plus lines are created altogether in a plasma chamber. Today, we will introduce an experiment method to find the best equipment settings, the method of response surface. Reactive ion etching is a microchip silicon wafer etching technology microfabrication. It uses chemically reactive plasma to remove patterned silicon dioxide film deposited on wafers. The plasma is generated under low pressure vacuum by radio frequency electromagnetic field, with chemical gas vapor injected in. The right combination of radio frequency electric field power, the pressure of the vacuum, and the hydrogen bromide gas injected into the etched chamber are the key factors led to high-quality silicon wafer. Engineers will need to ensure the profile of the polycrystalline silicon gates be isotopic. That is, the walls of etch lines should be vertically perpendicular to substrate in all directions, anywhere on a wafer. In this study, the engineers would like to find the right processing settings of these etch equipments. As this is a $1 million business, we are going to help them using design of experiment methods. Here are the cross-sections of finished polycrystalline silicon gate profiles under scanning electron microscopy. The ideal, or best outcome, is the top profile where the vertical walls are isotopic, or straight perpendicular rising from the silicon substrate. This type of profile has the best electrical channel length distribution, and therefore the fastest microchips. The second profile came with severe undercut under the photoresist cover upon plasma etching. This undercut is serious defect. The wafer may turn out to be scrapped if too much undercutting is present. The third profile is with a wider base or line growth. This defect is not as severe as the undercut. The overgrowth should be avoided as well. The difference between the cross-sectional top and bottom line width is called delta, with undercuts at negative and overgrowth positive values. In other words, engineers and researchers will need to find the best etch equipment settings to achieve the zero or slightly positive average delta values on a wafer. In practice, the ideal value is between 0.02 and 0.05 micron. Negative values is unacceptable. Let's face it, if you do experiments, you need a design. Otherwise, you might spend a lot of time and money and may not even find a solution. Design of experiments, or DOE, is a systematic way to discover how physical factors impact outcomes. In practice, it saves a lot of research time because experiments are easier with existing lab research equipment than starting a theoretical research altogether. Almost any researcher can set up experiments, but not becoming an expert on something they only need once. The key here is how to do the experiment the correct way. There are two steps in experiment study. First, design an experiment. Second, analyze the experiment data. For step 1, you only need to understand the basic DOE principles. There are computer programs today help you design the right plan for you. For step 2, you will need some basic statistical knowledge and a good computer program to help you, such as R. Don't worry, follow my series of videos, you will gain these skills quickly. Analyzing experiment data is the same as analyzing any other statistical data. I will show you today how to accomplish this in R. We use R because it is open source and always employs the latest techniques, but you can use other computing tools of your choice. Response surface methodology, or RSM, is a type of DOE. It uses a sequence of design experiments to discover the best variable settings lead to an optimal response or region. RSM usually starts with the first-order factorial or fractional factorial experiment to identify among candidate variables the ones that affect the response variable of interest. Then proceed to a more complicated experiment design such as the central composite design, or CCD, where you find a second-degree polynomial model. We see here the fitted surface in the case of two factors. There are either peak, hillside, rising ridge, or saddle point. Historically, RSM has led to huge scientific and technological breakthroughs, therefore are considered as core industrial competency. The central composite design, along with box-bunken design, are the most widely used designs for RSM. CCD contains an embedded factorial or fractional factorial design with center points. Then, these designs are augmented with a group of star points to allow estimation of curvature. Let's take a look at this two-factor CCD design. Engineers began with the full or fractional factorial experiment and identified two important factors, then augment the experiments by performing on the star points along the axles. The star points represent new extremes for each factor. The combined settings become a CCD plan. Similarly, for a three-factor experiment, the final CCD is a combination of cube points obtained from factorial designs combined with star points. There are three important properties with the CCD. They are, first, orthogonality. That is, the individual effects of all factors are estimated independently without combining, with minimum variance, and the estimates are uncorrelated. Second, rotatability. That is, the design points are rotating about the center of the factor space. Third, uniformity. That is, the center points are uniform in precision. For the wafer study, engineers have conducted factorial experiments and have determined the factors impact wafer line size delta. These are radio frequency, electric power for the plasma. Second, the pressure of the chamber vacuum. And third, the hydrogen bromide gas concentration injected into the vacuum. Wafer feature density is also known to impact line size delta, but it does not interact with other three factors. Other variables, such as gas flow speed, temperature, and magnetic field, are less significant, therefore will be treated as noise variables. Wafer feature density is a categorical variable. We use code 0 for low density and 1 for high density. There is another factor, the feature proximity on a wafer, that is, how close the features are positioned in a wafer. For this solution though, let's do all experiments on only the closely featured wafers. We will expand to low proximity wafer using a more complicated model in a future video. The RSM model we intend to fit is the quadratic form model, with x1 be the RF power, x2 the vacuum pressure, and x3 the hydrogen bromide concentration. We will repeat the design for wafers with high then low feature densities. We control feature density in the final model. The range of the factors are as follows. RF power between 120 to 180 watts. Can be as low as 100 or as high as 200 watts to the extreme. Vacuum pressure is between 20 to 30 millitorr. Can be as low as 15 and as high as 35 millitorr. Hydrogen bromide concentration should be between 10 and 20% and will tolerate up to 25%. We will create the CCD plan and analyze the experiment data using R. Let's open R Studio. Step 1. We need to create a central composite design. We use the RSM package. In case you have not installed it, download a copy from RCran repository. We can use the CCD function from the RSM package. We first specify a model formula. Only need to specify response and design variables. Then the number of center points in the cube blocks and star blocks. As we run all in one block, so we have 4 and 0 here, no repeats on star block. We need a rotatable plan. We also need to specify how the plan will convert the input variables from the original to the coded variables. To convert to coded -1, 0, 1 values, we will need to subtract the mean from the variable, then divide it by half of the range. Yes, we want randomized run order. Say true. We also want to run all experiments in one block. Take a look at the final design. Each design, values of line size delta are missing. We will proceed to hand the plan to engineers to conduct the experiment. Wafer lab engineers conducted experiments, saved data in the design plan column line size, renamed the dataset to close. We use the RSM function to analyze the collected data. What the RSM function does is that it feeds the experiment data to a linear model of your choice. Any statistical techniques required to feed the right linear model apply here. We'll go into more details on that in a separate video. But here, we have found the quadratic model with the control is a good or close to good model after some explorations. We first specify the model formula, the response variable, then the SO function, or the quadratic form with 3 design variables: power, pressure, and hydrobromide concentration. Make sure you use the coded version of the variables, not the original. Then we add the categorical feature density indicator outside the SO function quadratic form. Tell the name of the data frame. There you go. Take a look at the fitted results. For model diagnostics, we take a look at the QQ plots of the residues. The QQ plot indicates model residues are mostly normal, with the bound of 95% confidence interval. Take a look at the residual versus fitted values. The random pattern is mostly intact. Along with the model summaries, we think the model fits the data reasonably well. Here are the fitted response surfaces, 2 factors at a time, with the third at its mean level and feature density at a high level. We could locate the operating regions visually. Surface area matching our ideal average delta between 0.02 and 0.05 micron corresponds to the power settings between 100 and 200 watts. The vacuum pressure should be near the lowest levels, around 17 millitorr, and the hydrobromide concentration should be near the highest regions between 20 to 25%. We should avoid any region that led to 0 or negative delta, where H-line undercuts are prevalent. The curvature low is in this region, therefore it should be ignored. Since the overall trend is positive monotonic for the delta versus power and hydrobromide concentration, and negative versus pressure, as seen in the 3D plots, we should conclude the higher the power, the lower the pressure, and the higher the concentration of hydrobromide gas within the allowable limit settings will result in the best delta value between 0.02 and 0.05 micron. In this RSM study, we investigated the etching equipment settings that will lead to the best wafer line size through experiments following a central composite design for RSM. With this discovery, we're well on our way to produce the best quality microchips. Hello, competitors! If you are interested in this and future educational videos, please subscribe our channel. Find the data and R codes in this tutorial in www.researchknowledge.com. Write in the comment section if you have a question. Thanks for watching.